Welcome back to the course on memory device technology for AI/ML computing. I'm your instructor, Dr. Shubhadeep. Let's try to recall what we had studied in the last session. In the last session, we saw how memory array architecture is being facilitated. We saw the basic definitions of word line, bit line, word length. We also saw that it may not be a very great idea to scale memory arrays to go to this kind of a rectangular architecture by vertically stacking the different words. This can have several disadvantages, such as difficulty in floor planning and in read-write access times and energy consumption. Therefore, the suggestion was, why don't we move to more reasonable squarish array with an aspect ratio of 1:1. And the fundamental constraint that we put is the number of bit lines and the word lines for a square matrix have to be equal. However, this kind of folding of the rectangular array into the squarish array will complicate matters when it looks from the perspective of peripheral design. And today we will try to see how these square arrays are organized and also what are the peripherals that are needed to read and write data efficiently from these square arrays. So let us begin. So today we will look at how is this square arrays facilitated. And to understand how the square arrays are facilitated, we have to introduce a new technical term or a new concept of a page. Just like our books have a particular page, our books or our physical notebooks or textbooks are organized in physical pages. In a similar way, a square array also consists of individual pages. Now, what are the number of pages in a memory array? In the most general case, the number of pages in a memory array is the same as the word length which is being expected from the CPU. Try to recall, the word length is nothing but the size of the data that is expected from the CPU once it asserts a particular address on the address bus. So the size of the number of pages in the memory element is nothing but equal to k, right? But as you can imagine, since the number of word lines and bit lines are the same, the number of bit lines have to drastically increase. This is because in the previous example of a rectangular array, the number of bit lines were nothing but the number of was nothing but the word length, which was k. Now, since the word lines have reduced, the bit lines need to increase. So, therefore, the bit lines are much more compared to k, or the number of pages. So, therefore, the way it is organized is within a single page, I have indicated the pages with dashed lines in this square architecture from page 0, page 1 right up till page k minus 1. So total number of pages is k. Within each page, there is 2 to the power of m columns, right? So within each page, there are 2 to the power of m columns, and therefore the number of bit lines is equal to k into 2 to the power of m. Why is that the case? Because there are k pages, each containing 2 to the power of m columns. So the number of bit lines or the number of vertical green lines in this square array will be equal to k into 2 to the power of m. At this juncture, it is very important to understand the rationale or logic of why memory arrays are organized in form of pages. This is because each page will give one bit of information to the output data bus. What I essentially mean is, if there is an expectation from the CPU to get k bits of information, each of the k pages will give 1 bit of information each. Essentially, page 0 will give the 0th bit or the LSB of the data which is asserted on the data bus. Similarly, page 1 will give out the information about data 1, so on and so forth. Page 32 in our case, or page 31 in our case, will give you data for the most significant bit. Now, how is this facilitated? Please recall that there are k pages, and within k pages, within each of the pages, there is 2 to the power of m columns. So how do you select one data bit or one relevant bit line from the 2 to the power of m available bit lines within each page? After understanding that the total number of bit lines is k into 2 to the power of m, let us ask the question, what will be the number of word lines? So the word lines very simply will be 2 to the power of n. Now it is important to understand the total value of 2 to the power of n will be much less than 1 million, because from a rectangular array we have now gone to a square array. Just like the number of bit lines are increasing from k to k multiplied by 2 to the power of m when we go from a rectangular array to a squarish array, the number of word lines definitely have to shrink. So this 2 to the power of n will be much less than a million, or n will be much less than 20 when we take the example we were considering. Additionally, since we are talking about the square array, we have discussed that the number of word lines and the number of bit lines will be the same. So 2 to the power of n, which is the number of word lines, will be the same as k into 2 to the power of m, which will be the number of bit lines. This will be one of the important equations that we will use to find out what will be the exact values for m and n for a particular array design. The next thing to consider is what is the size of the memory array. In our previous example, it was 32 megabit. How do we derive the second set of equations? Since there are two unknowns m and n, we will need two equations. So the second equation is set by the size of the memory array. As we know, the size of the memory array is determined by the number of individual cells. Also, we know that between each word line and bit line, at the intersection of each word line and bit line, there exists a memory cell. Therefore, the multiplication of the word line and bit line will give you the total size of the memory array, which is nothing but k into 2 to the power of n into 2 to the power of m, which is nothing but k into 2 to the power of m plus n. By putting these two constituent equations, it is possible to calculate m and n for a particular design, and we will see how to do that in a solved numerical in the next class. Okay, now that we have understood this, how is the array organization done? The next important question is, how is the peripheral design done? And as you can understand, the peripheral design has to change quite drastically. The peripheral design has to change drastically because earlier the number of bit lines were just k, whereas now the number of bit lines is k into 2 to the power of m. Please try to recall that within each page there are 2 to the power of m lines. However, for one read or write cycle, only one of the 2 to the power of m lines are actually relevant. So which is the digital element which can select one output from 2 to the power of m columns? And as we know, this is exact opposite of a decoder. It is called a multiplexer from our study in digital design systems. So a column mux is essentially which is used to select one data output from 2 to the power of m lines. And this is facilitated by supplying m bits. Just like the decoder, you had n bits and you were selecting one of the 2 to the power of n lines. In a column mux, the input is 2 to the power of m bits and m select lines. These m select lines decide which of the 2 to the power of m inputs actually are routed to the output. In this fashion, 2 to the power of m lines or word lines, 2 to the power of m bit lines coming from individual pages, each of the k pages are then converted into k bits using the column mux. And these k bits are finally what is fed to the data bus. Also, we should not forget that there are 2 to the power of n lines when it comes 2 to the power of n word lines or select lines. So in addition to this column mux, we should now have a row decoder to find out which of the 2 to the power of n word lines are selected through the address bus. So earlier, if you remember, our address bus had just one component which was sent to the address decoder. Now the address has two objectives: the input to the row decoder and also to the column mux. And in this generic design, the row decoder you are sending n bits and the column mux you are sending m bits. So the total size of your address bus now becomes m plus n bits. And this is how the memory array peripherals are also becoming complicated. So this, to recap our discussion, since folding the rectangular array involves increasing the number of bit lines from k to k into 2 to the power of m, which is organized as k pages, each having 2 to the power of m columns, you need column muxes to select which of the relevant bit lines are to be picked for one data cycle amongst these 2 to the power of m, and this is facilitated from the column mux. And this is how you see the memory array peripheral architecture is also getting more complicated. Okay, once we have understood both the array organization and the peripheral architecture, let us try to see how simple read and write operations are facilitated in this kind of design. So the first thing we will do is look at the read operation. So what is the expectation from the CPU during a read cycle? The expectation from the CPU is that it will be supplying an address consisting of m plus n bits, and it will receive information in form of digital bits which is same as the word length, which is k. So on the address bus it will assert m plus n bits, and on the data bus it will get information worth of k bits. How is this done? So as we discussed, the first thing to do is set an appropriate address consisting of n plus m bits. So what happens when you set n plus m bits? First thing that happens is the n bits are first fed into the row decoder. As n bits are fed into the row decoder, one of the 2 to the power of n word lines is selected through the row decoder. So you see many of these horizontal word lines. When an appropriate address is set, one of them is effectively selected. So as we had seen in the case of the DRAM, all the cells corresponding to a particular word line get selected when the row decoder selects one out of 2 to the power of n select lines. Here it is important to realize, as you make array sizes larger, we discussed this in the previous class also, that these bit lines and word lines, although they might be copper interconnects, as you increase the size of these interconnects, it's not just the resistive element, but the entire impedance that must be considered. So in addition to the resistive element of these word lines, you have to also consider that they have some capacitive component. Any real life wire will not just have resistance, but it will also have capacitance. And these capacitance effects start playing a very important role when you shrink the size of these interconnects and start operating at higher frequencies. So here we are going to change the terminology of applying some value to the word line. Earlier, the terminology we were using was that we assert the word line. When we use the terminology assert, we assume that the word line consists only of resistive element. As we just discussed, at high frequencies and at scale devices, that may not necessarily be true, and therefore we use the word charging. Since there is a capacitive element to it, we have to use large write drivers. So this is where we introduce the term write drivers. As we will see very soon, write drivers are nothing but large pass gate transistors which can supply a lot of current to charge and discharge these word lines, and we will see bit lines also very quickly. So in essence, how quickly you can assert the word line will determine your read and write speeds. So if you want fast charging times, you will have to use larger area transistors. This is where we see the first time that there is a very clear trade-off between latency and area. If you want low latency, you will have to compromise with a larger area. So these write drivers, which are kept next to the row decoder, ensure that the word lines are charged very quickly or pre-charged very quickly. The next thing that we do is ask the question, once the word line enables all these cells on a particular row, what is the output that we get on the bit line? A naive expectation would be that we will either get 0 or 1. But please try to understand. Look and imagine what would be the size of an individual small element which is sitting at the intersection of bit line and word line. It will be a small tiny element compared to the size of the bit line. So amount of current it can put into the bit line or take from the bit line would be very, very small. Therefore, it is not correct to expect that a small element will be able to charge and discharge these huge wires. In reality, we see that the output on the bit line is not 1 or a 0, not a clear 0 or 1 value, but small analog voltage which changes. If it goes to 0, the bit line gets discharged. If it tends to 1, the bit line seems to get charged. And this is where additional peripheral circuitry becomes absolutely essential. And the name of this additional analog peripheral circuitry is called sense amplifiers. So what is the job of sense amplifiers? The job of these sense amplifiers is to detect the small analog voltages and understand whether the value 0 or 1 is written in the corresponding bit which is connected to the bit line, and pin this value, to sense this small analog voltage and amplify it to rail, either 0 or 1. And this is where sense amplifiers become very, very crucial. So simple question I want to ask is, from your basic study of analog devices, what is the simplest sense amplifier that you can think of? Most of you might have studied about open loop op amps. As you know, in an open loop op amp, if you apply some reference voltage and give an input voltage at the non-inverting terminal, because the open loop gain is very, very high, a small positive change over Vref quickly pins the output to saturation plus VCC, and a small negative differential over the Vref quickly pins the value to negative VCC. So the simplest sense amplifier that we can think of is an open loop op amp where the reference voltage is applied to the inverting terminal. This kind of circuit can very quickly detect small positive or negative movements over the reference and pin it to either plus rail or the minus rail. However, you have to realize that a single op amp consists of 20 transistors. See the number of bit lines that are coming out from the array. It is k into 2 to the power of m. K into 2 to the power of m analog voltages are actually coming out from the memory array. If you start using 20 transistors for a sense amplifier for each of the k into 2 to the power of m lines, your peripheral circuitry comprising of your sense amplifiers will become very, very large, and therefore you need a simpler design, and that is what we will look at in the next class. Also, you see that there is something called write drivers, which in the read cycle are disabled. What these write drivers are, we will look at it in the next portion. So as a result, these k into 2 to the power of m analog voltages are fed into equivalent sense amplifiers. The job of the sense amplifiers is to pin these values either to 0 or 1, and through the column mux, which has its in select lines connected to the address, one of the 2 to the power of m columns from each page are then routed to the data bus through the column mux. Okay, so this is what concludes how generic read processes are facilitated in a memory array. Next, we will study the write process. So what is the basic expectation in the write process? The basic expectation from the CPU in the write process is that the CPU will give two outputs, the address and the address bus, which is consisting of m plus n bits, and k digital bits, which is asserted on the data bus. The expectation is the relevant word in the memory array gets updated or gets written into. So let us see how this is facilitated. So the first thing that we do is, as we discussed, we set k bits in the data bus and n plus m bits in the address bus. Since we are supposed to write some values, and the only way to write values is to assert values in the on the bit lines, the first thing that is done even before the word lines are asserted is that these k relevant bit lines are charged. How are the k relevant bit lines charged? This is done through write drivers, which is there after the column mux. These write drivers become active in the write cycle, and the sense amplifiers are disabled during the write cycle. So these write drivers, along with something called the write mux, which we will describe very soon, are enabled, and these write drivers select which relevant bit line from the 2 to the power of m bit lines in each page are to be written into. Therefore, the values are pre-charged, either 0 or 1 is pre-charged into the bit lines only for the corresponding 2 to the power of 1 of the 2 to the power of m bit lines within each page. Please note here, often it could be confusing that there are two kinds of muxes in this design. One is the column mux. The objective of the column mux is to decide which of the 2 to the power of m bit lines are to be written into, and there is another mux called the write mux. The objective of the write mux is, during the write cycle, enable the write drivers and disable the sense amplifiers. During the read cycle, this mux is disabled and only the sense amplifiers are active. So after this pre-charge of the k bits is done, the next part is to select or enable the appropriate word line. When the appropriate word line is now enabled, the data select pin goes high, and therefore the storage node is now connected to the bit line. And through a process, the voltage or the information is transferred from the appropriate bit line into the storage node. And this is how write is done. Please important to note that the data gets written only in the appropriate row which is selected by the word line. So through these really complicated sequence of events, both read and write is facilitated. It is important to note that apart from all these peripheral circuitry that we discussed, such as the row decoder, the column mux which form the digital portion, and the write drivers and the sense amplifiers which contribute in the analog portion of the peripheral architecture, the sequencing of events for read and write is also handled by the memory peripheral architecture and design. So to conclude our today's class, we saw that memory peripheral controller, which consists of these different digital and analog elements and the intelligent circuitry to do the sequencing for read and write cycles, consume a significant area into the entire memory chip. So earlier we were feeling that only the memory array is what consumes a lot of area, but now we saw that through different logical constraints, we saw that memory peripherals are also a very important part. So let us conclude our discussion today. What we saw essentially is how rectangular arrays are converted into squarish arrays where the number of bit lines and word lines are the same. We introduced the very important concept of a page. The page is equal, the page in a memory array is equal to the word length. Each page consists of 2 to the power of m columns. The responsibility of selecting which of the 2 to the power of m columns is on the column mux. Therefore, and which word line is selected is on the row decoder. So the address now consists of n plus m bits. And also we saw the importance of having sense amplifiers and write drivers. In the next class, we will do a deep dive of sense amplifiers, write drivers, and hopefully solve a specific example which will teach you how to derive the size of the address and the data bus or individual n and m bits. Thank you very much.